Hey everybody, and welcome to the linear and angular velocity video. In this video today, what we're going to talk about is we're going to go over four main formulas that are going to help us figure out what our linear and our angular velocity are. And then we'll see a couple examples about how to use these formulas. So let's get going. So here are our important formulas here. So the first one that we're going to go over is going to be for angular velocity, also known as angular speed. So that's, well, this guy is the mu here. So this is going to be our angular velocity. And you'll see it also in textbooks or problems. They will also say speed. So angular velocity, angular speed. And what that is starting from the center. So let's say I start here and I'm rapidly opening up and then I end over here. Angular velocity is asking how far, like angular, radian, degree, whatever, did I open up as a function or per ratio over time. So theta here is the central angle. So how far did I open up? And t is time. And angular velocity you'll see is degrees per second, radians per second, per minute, per hour, per day, per whatever unit of time we're talking about. So it could be degrees per minute, radians per minute, whatever. That's how angular velocity is measured though. Degree measure or radian measure per unit of time, okay? And it's, basically, hey, how fast are we opening? That's it. How fast are we opening? That's angular velocity. The next thing we're going to look at is linear velocity. So that's the v here. So the v is linear velocity, also known as linear speed. So we denote that with little v. S is the distance that we traveled around the circle. So S is distance. T is again time. So all the variables are going to be the same. So every S is going to be the same. So this S is also distance. This T is time. This T is time. You'll see this V is still linear speed or linear velocity. Every variable is going to be the same thing. So distance, what do we mean by that? Well, we mean, hey, if I start, and we're talking about as we travel around some circular region, some disk region. So if I start here and I travel around and I end up here, that's S. S is the length that I traveled, also known as arc length, right? Which is why we have the arc length formula here, because we could figure out S because S is the arc length, right? So that's what S is. S is the distance that we went around the circle, and T is still time. So the distance we went around as a ratio of our time, right? So you can think about it as feet per minute, inches per second, miles per day, whatever, distance over time. That'll give you the linear velocity. Basically, how fast are we going around the circle? So angular velocity, how fast are we opening up? Linear velocity, how fast are we going around the circle? And then the other two equations relate, oops, I want that back. So like I was saying, S is still distance around the circle, also known as arc length. So this is the arc length formula, and the theta is still the same. So the theta is still, the theta is still the angle that we opened up. This distance here would be S. R is the radius. So R is the radius, theta is the angle that we opened up here, also known as the central angle, and then S is the distance around arc length. Okay, so this is the arc length formula. And then the last formula is how linear velocity and angular velocity relate to each other. So linear velocity is equal to the radius of whatever circle, disk, or whatever you're on times the angular velocity. So angular velocity times radius will give us linear velocity. So in the next couple examples, we're going to go through all of these formulas and we're going to show examples of exactly how to use each one of them, and sometimes we'll actually use more than one. So point P sweeps out of a central angle theta as it rotates on a circle of radius r as given below. Basically, we have a point on a circle, and we're going around the circle. What is the angular speed? All right, well, there's our key hint. Angular speed, that's going to put us in this equation here. So let's fill in what I know. So angular speed is equal to theta over time. Theta is 18 pi over time, which is 3 pi seconds. So our mu, then pi's cancel. 18 over 3 is 6. 6, and then are we in radians? 6 radians per second. Okay. Angular velocity. Now let's look at linear speed. So find the linear speed. Okay, which one of these equations give us linear speed? This guy here. Of a point moving with uniform circular motion, in other words, our angular speed is fixed. If the point covers a distance s in amount of time t, where s is 16, okay, so linear velocity is equal to s, which is 16 feet, over t, which is time, which is 4 minutes. So units are important here. So 16 over 4 is 4, so we would have 4 feet per minute. And that would give us the linear speed. So see what I mean? Linear speed, linear velocity, you'll see it the same way in this particular arena. Okay, what about this guy? So same setup. P is moving with angular velocity mu on a circle of radius w. Find the distance s traveled at the point in time t. Answer exactly. So we have our mu, 4 radians per second. R is 5 inches, t is 3 seconds. What are we trying to find? We're trying to find s. So we do have one formula for s. S is going to be theta times r. So we know s equals theta times r, and we know r right now, r is 5. But we don't know theta. So is there another formula out here that could help us figure out theta with what we have here, and then we could plug it back in? There is. So we're going to use a combination of the angular velocity and the arc length formula. So I know mu, it's 4. 4 radians per second is equivalent to theta, which we don't know, but I do have time. 3 seconds, right? Multiply both sides by 3 to cancel it out here. I would get 12, and seconds over seconds would cancel out, so I'd have 12 radians, 12 rad. So theta is equal to 12 radians. Okay, cool. Let me plug that in there. So now S is equal to 12 radians times 5 inches. So S then is equal to 60, and then since S is a distance, 60 inches. So that's how we figured out S. So we used a combination of the angular velocity formula and the arc length formula to get us the theta we needed, and then we used the theta in the arc length formula. So we get creative in this, right? Because there's so many, our variables get used more than once. So you may need to use one formula to help you solve another formula. So don't just think there's always going to be, oh, one formula is always going to get me the answer. You might need to work and tinker a little bit with some other formulas to get some other variables that you need figured out, and then you can ultimately find what you need. So now let's look at, so we're rotating with uniform motion on a circle of radius r. So find v. Okay, so we want to find v. So who finds us v? That'll find us v, and that'll find us v. So that's our first hint. We're looking for v. So we probably are going to dance in one of these two formulas. So we have an r, okay, and we have a mu. So we have an r and we have a mu. So that means I really want to use this formula because I know r and I know mu. So v then is going to be equal to r, which is 5 inches, times mu, which is 4 radians per second. So velocity then is going to equal 20, linear velocity, 20 inches per second, right? Because it's 5 times 4 gives us 20 inches over seconds, 20 inches over seconds. And that's how we found v, because we realized, hey, we want to use this formula here, which relates angular velocity to linear velocity. All right, let's look at an application problem. So we have the Earth rotates 1 complete revolution every 24 hours. So 1 revolution per every 24 hours. Okay? Since the axis of the rotation is perpendicular to the equator, you can think of a person standing on the equator as standing on the edge of a disk. This means we're taking what was a 3-dimensional problem, we're putting in a 2-dimensional problem. So they're essentially saying you can think of yourself as being on a disk and rotating around. So now this becomes a circular problem instead of a spherical problem. And then we rotate all the way around every 24 hours. Find the angular and linear velocity. Okay, angular velocity is this guy here. So mu equals theta. What is theta, right? How far around the circle did I go? I went all the way around. Okay, how far is all the way around the circle as far as angles go? All the way around the circle was 2 pi because we went 1 revolution, right? We didn't cut it off and go like 3 pi over 4 or 5 pi over 6. We went all the way around. All the way around is 2 pi. So we went all the way around. So that's theta. And our time, we were told our time in 24 hours. So then our angular velocity, 2 over 24 is 12. 12 pi per hour. Okay? So there's our mu. And then what else do we need? We need linear velocity. Okay. What else do we have? We have the radius of the Earth is 4,000 miles. Okay. So I know mu and I know r, and I need to find v. Well, I know mu, I know r, and I need to find v. So I really want to use that formula there. So v is equal to r times mu. Okay, r, 4,000 miles times mu, which is 12 pi per... Oh, excuse me. I don't know what I was doing down here. It's not 12. Hello? 12 over 24 is 1 pi per 12 hours. So this is going to be pi over 12. So this is pi over 12 here, which means this needs to be fixed. Pi over 12. There we go. Okay, now let's solve this. So this is basically, looks like 4,000 pi over 12, reduce, divide by 4, divide by 4. We would get 1,000 pi over 3, and this is going to be miles per, what do we hear, hours. And that is our linear velocity, and that was our angular velocity. So I hope those examples were able to shed some light on how to use the angular and linear velocity formulas. And we also looked at arc length, and we looked at how linear velocity and angular velocity relates as well. As always, if you have any questions, please don't hesitate to ask, and I'll see you guys next time.